Alright, this is your video on calculating average atomic mass. In this video we're going to cover why mass numbers are not whole numbers, the proper unit for the atomic mass of an atom, and then how to calculate the average atomic mass, of course, and then how to determine relative abundance of isotopes for a particular element. So I'm going to go ahead and talk a little bit about each one of these things. One, why are mass numbers not whole numbers? So if you take a look at this image right here, you notice that this is our mass number, okay? This is our atomic number, okay? And from class, we realized that if we had an isotopic notation of chlorine, and then we have 35.453, and then 17, right? And I said, okay, we'll use this information to determine the number of neutrons. Well, if I do that, I'm going to end up with, well, not a whole number. And what that is going to result in, let's do the math real quick. Okay, I'm going to end up with 18.453 neutrons. Now, hopefully that should ring a bell and go, or send up a red flag going, well, that doesn't make sense. How can you have a part of a neutron? It's a subatomic particle. I can't have part of a proton. I can't have part of an electron. So why can I can't have part of a neutron either? And you can't. So really what this number right here is representing, it's not just representing the mass number, but more of an average atomic mass. Okay? We learned in class there are different isotopes, right? Well, the different isotopes, if you were to average out the masses of those different isotopes, the average is the mass number. Okay, so please don't think that you can end up with fractions or decimals for the number of neutrons. That would be very, very, very wrong. Okay, so the that's why the mass numbers are not whole numbers. They're representing an average atomic mass or average mass, and just so you know, that mass is, or that average is a weighted average because not all isotopes are appearing in the same abundance, and we'll talk about that soon. Now, if I was to go, if I was to ask you what is the unit for atomic mass, well, it's, oddly enough, the atomic mass unit, or AMU. Okay, so AMU is the is the unit for atomic mass unit. Okay, and what it represents is, or the quantity of an atomic mass unit is, we'll go and put over here, is 1/12 the mass of one atom of carbon-12. Okay, so that's what defines what an atomic mass unit is as far as how much mass that is. Okay, obviously this is a very, very, very small amount. Okay, atomic mass units, AMUs, are much, 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 much smaller than even grams or even milligrams or centigrams, milligrams, grams. Anything that we've dealt with in mass, AMUs are much, much smaller than that. Okay, now to calculate our average atomic mass, okay, in order to calculate this value right here, as far as saying, well, how do I get that? There are two things that you need. Okay, let me go ahead and clear the board here real quick. So hopefully you got it all down. All right, the stuff that you need the mass of each isotope, right? And you need to know the abundance of each isotope, and the abundance is given in percentages. Okay, so the mass is going to be given in AMUs, and the abundance is given in percentages. Okay, and we're going to go ahead and do a problem like that now. All right. If you don't have the abundance and you don't have the percentage, you cannot do the problem. All right. So let's take a look at the natural abundance for boron isotopes. It is 19.9% boron 10 and 80.1% boron 11. Okay, so here I have two pieces of information here. I have my percentage which is my abundance, and it's boron 10, which gives me the mass of 10 AMUs. Okay, and the same thing here, I have an abundance here, and in a percentage, and then I also have 11 AMUs for the mass of that particular isotope. Okay, so what I'm going to do is I'm going to set the problem up. Okay, and the first thing I want to do is get rid of my percentages. I want these to be in decimals. Okay, so I'm going to go for boron 10. Okay, so let's go 10, there's boron. Okay, for boron 10, I'm going to go 19.9 divided by 100 is going to give me 0.199. Okay, this is going to be important for sig figs, so make sure that you get rid of the percentage and divide by 100. Okay, same thing for the boron 11. Okay, I'm going to take 80.1 and I'm going to divide it by 100. Okay, and I'm going to end up with 0.801. Okay, now I then realize that, okay, I have this abundance value. This is my abundance value. Now, my abundance value is normally given in percentages. Again, you got to make sure you get rid of that. Your abundance in your calculation needs to be as a decimal. Okay, so divide by 100 to get rid of the percentage. And then all I do is I multiply by the AMUs, or I multiply by the mass of the isotope. In this case, for boron 10, it would be 10. And then for boron 11, it would be 11. Okay? Get these guys right here. So I do that math. I end up with 1.99. Right? And then here I end up with 8.811. Okay? So in doing this, okay, these numbers right here, okay, these right here are exact numbers, so you don't pay attention to sig figs for them. But when you do your next step, which is add these two values together, right, you are going to be paying attention to sig figs. So when I add these together, I'm going to end up with 10.801. Okay, now remember, when it comes to adding with sig figs, whichever one has the least precise number. So I have 2 decimal places here, I have 3 decimal places there, which means my final answer needs to have only 2 decimal places. So my final answer, I'm going to get rid of this 1, and the average atomic mass is 10.80 AMUs. Okay, and that's it. Okay, obviously, if I have more abundances, okay, like if I have 3 different isotopes, then I need to do 3 of these right here. Oops, not quite. Well, yeah, 3 of those right there. Okay, here I only have 2, so I have 2 abundances, so I only do 2 problems. I'm adding 2 of these numbers together. I'm adding this number together, and I'm adding this number together to get a final sum. Okay, now it's important to note that if your abundances, okay, because sometimes I won't give you all of them, I'll give you all of them except 1, okay, you need to make sure that all of your abundances add up to 100%. Okay, so this right here, 19.9 and 80.1, you add those 2 things together and they're going to equal 100%, right? Well, likewise, when I add this number right here to this number right here, I have, or I better have, 1. Okay, and if I don't, then there's a problem somewhere in my math. All right, so that's how you calculate an average atomic mass based on the abundance and the mass of each isotope. Now, the other activity that, or the other practice or skill that I'm gonna have you guys do is if I give you the average atomic mass, which is going to be given in the periodic table, okay, is I want you to tell me what are the relative percentages of an element. Okay, so what kind of information do I have? Well, I know that the average atomic mass is 35.453. Okay, and I have the masses of the isotopes. Okay, well, like in the last problem, I knew that the abundance percentage of this and the percentage of this, if you add them together, they must equal 100%. Okay, and the average being 35.45 would be my sum of my problem. So what we're going to do is we're going to set it up, and this is simply algebra. Now, before we get too far into this, okay, I want this to be very, very, very clear. Okay, you are not, do not apply sig figs here. Okay, all I want you to do is follow instructions as you go. Do not apply sig figs. All right, so don't apply sig figs. Period. For this problem, when you're trying to calculate percentages, don't apply sig figs. All right. Looking here, I know that the chlorine 35 plus, the percentage of chlorine 35 plus the percentage of chlorine 37 is going to equal 100%. Okay, I know that because that's representing all of the chlorine. Okay, well, if I was to break this down algebraically, I know that 35 is the mass. Okay, and just like I had in my last problem, I go the mass times the abundance. Well, in this case, since I don't know what the abundances are, I know that the abundance must be some number. So how do we represent some number? Well, we represent some number with x, right? Now, if we follow along with this right here, and remember that the percentages must be removed and they should be decimals, just like here where this 0.199 and 0.801, they must add up to 1. Well, another way to write that would be 1 minus 0.199 would be the 0.801. Okay, so here I'm going to have 35x, and then I'm going to add, okay, 37 times x minus 1, because that's going to represent the abundance of the remaining isotope. Okay, so I know that x is going to be some value, and then I know that because those are the only two amounts and they must add up to 100, or in this case 1, because I'm going to get rid of the decimal, I'm going to divide out, right? I'll end up with, oops, excuse me, there we go, 1 minus x, sorry about that, okay? And I know that the sum of this is going to equal 35.453 AMUs, okay? So if I was to do my distribution, I end up with 35x plus 37 minus 37x equals 35.453 AMUs. All right? So I reduce down, I end up with negative 2x equals 30, oops, negative 3x plus 37 equals 35.453. I subtract 37 from both sides, and I get negative 2x is going to be equal to negative 1.547. Okay, you're thinking, well, this is getting ugly. Well, remember, this is as decimals, not as percentages. So when I divide this out, divide by negative 2, and divide this by negative 2 on both sides, that gets rid of my negative 2, okay? And then when I divide this out, I'm going to, let's go ahead and just draw this line right here in a little open space. I'll end up with 0.7735, okay? Well, what does that mean? That means that x is equal to 0.7735, which is 77.35%, right? If I multiplied that number by 100, I would get 77.35%. So the mass, or the abundance of chlorine 35 is 77.35%. And if we follow this rule right here, okay, the abundance of chlorine 35 plus the abundance of chlorine 37 must equal 100%. So I would go 100 minus 77.35, and I end up with 22.65%. So that's how we calculate the abundances, or the abundances of, or the relative percentages of an element if you have the the average atomic mass, and you have which isotopes and the masses of the isotopes. Okay? So, last thing is use this information to determine what was the average atomic mass of your sample of Beano. Now remember, you need the mass of each isotope, which you did. In this case, you had 5 different isotopes, because you had 5 different types of bean. Okay? And you needed to know the relative percentages of each bean, or of each isotope. Okay? So, you have all the information you need, so give it a shot, and we'll talk about it tomorrow.